Hi there, welcome to Explain This, a podcast where we try to explain complex things in simpler ways for people of all ages. I'm your host Jun Kim, and today we'll explain to you what the deal is with prime numbers. And no, this podcast is not brought to you by Amazon Prime. Unfortunately, we're not quite at the level of being sponsored. Yet. Anyway, let's get started. If you paid any attention to maths class back in school, you've probably at least heard of prime numbers. Although, to be honest, nowadays, people are probably more familiar with the word prime from things like Amazon Prime, Prime Ministers, the prime of your life, and, of course, the almighty Optimus Prime. The word prime has the same Latin root as the word primal, primary, and even prima donna. It essentially means first, or best, or the beginning. So, what are prime numbers then? Are they the first numbers to exist? Well, close. In essence, they're the fundamental building blocks in the world of numbers. What do I mean by that? Well, you're about to find out in this episode. Without further ado, let's jump into explaining what prime numbers are to you as if you were a child. That's right, you may be a grown adult, but you still can't avoid elementary maths. Do you remember your times tables? You know, like 2 times 2 is 4, 2 times 3 is 6, and so on. This is called multiplying, where you can combine two numbers to make an even bigger number. Like if you have two sets of 6 eggs, then you have 2 times 6, which is 12 eggs total. The cool thing about multiplication is that you can undo it by dividing the bigger number. So if you have 12 eggs, you can divide it by 2, which leaves you with 2 sets of 6 eggs again. 2 times 6 is 12, 12 divided by 2 is 6. Easy as that. Yeah, I know you know all about multiplication and division, and I'm teaching you how to suck eggs, but it's important for the next part. Now, let's treat maths like a baking recipe. If 12 is a delicious cake that we're trying to bake, then 2 and 6 are the ingredients. We can call these ingredients factors. Some numbers are really complicated, like a souffle or a gingerbread house. They need lots of factors. But some numbers are super simple, like a basic cookie recipe. These numbers only have 2 factors, or 2 ingredients. In maths, you can divide every number by 1, because if you count one set of something, you'll have exactly the same amount. So this means that the only other factor for these recipes can be the number itself. For example, take the number 7. You can divide 7 by 1, and that's 7. Easy, same number. But you can't divide 7 by 2, or 3, or 4, or 5, or 6. So 7 only has 2 factors, 1 and 7. We call this kind of number a prime number because you can't break it down any further. They're like flour, sugar, and salt. They're the basic building blocks for making bigger numbers, or products. Okay, cool, big whoop. You can't divide them by any other numbers. So what's the dealio with prime numbers? Why do we care about them? Well, turns out because you can't divide them by any other number, they have some really interesting, unique properties, so you can use it to make really complicated secret codes out of them, so you can talk to people on the internet without other people eavesdropping. Cicadas use them too, so they don't get wiped out by other animals eating them. And scientists use them for all sorts of things, from quantum physics to making random numbers in video games. And lastly, you get to feel real smug and feel clever that you know about these special numbers when all your friends are living their dull, boring lives without the joy of maths in their life. The last one's not so useful, but it's pretty groovy. And we're back. So you probably remember something from maths class about prime numbers not being divisible by any other number other than itself and 1. Well, that's basically it. A prime number is officially defined as a natural number, that is, not fractions or decimals, and only has 2 factors. This means that, weirdly, 1 is not a prime number, because it only has 1 factor, 1. But 2, oh boy, now that's a proper prime number, because nothing divides 2 other than 1 and 2. The same goes for 3, and 4. Oh wait, no, 4 can be divided by 2, because 2 times 2 is 4, right? So 4 isn't a prime number. It's what we call a composite number, because it's made up of more than 2 factors. In theory, finding prime numbers sounds easy, right? You just have to check if you can divide a number by any other number. If you can, it's not prime. If you can't, all the way up to the number itself, then it's a prime. Easy peasy. Why do we even have a whole podcast episode based on this anyway? Well, this is how mathematicians have discovered larger and larger prime numbers for centuries, up until quite recently. We've actually known about prime numbers for a very long time. The earliest proper record goes all the way back to 300 BC when an ancient Greek mathematician named Euclid discussed them in his famous textbook, Elements. We'll talk a little bit more about Euclid later in the episode, so remember the name. Around that time, another mathematician called Eratosthenes came up with a clever way to find prime numbers. He suggested using a sieve method, now known as the sieve of Eratosthenes, which kind of sounds like a cooking utensil from Dungeons & Dragons. Now the sieve works like this. You can follow along with us if you have a pen and paper. Let's say we wrote down a list of numbers, starting from 1, 2, 3, and so on. Maybe up to 50 or 100, just to make it easier. Now the first one's a freebie. We already said 1 is not a prime number, so we can go ahead and cross that out. So we move on to the next number, which is 2. Can you divide 2 by anything other than 1 and 2? No? Good. We found our first prime number, so let's circle that. Now that we have a prime number, this is when the sieve becomes useful. What we can do is we essentially do the 2 times table and cross out every number on it. So that would be 4, 6, 8, 10, and so on. Because these numbers are obviously divisible by 2. You'll notice that all of these are even numbers, so there are no even prime numbers other than 2. Alright, once you've done this, we move on to the next number, which is 3. 3 is also a prime number, so we do the multiplication process again. Go ahead and cross out 6, 9, 12, 15, and every third number from there. You'll notice that when you get to 4, it's already crossed out because it's a multiple of 2, so we can skip that one. 5 is the next prime number, so now we cross out all the multiples of 5. And after a while of crossing out numbers, you end up with a small selection of circled prime numbers. These numbers you know can't be divisible by anything smaller than them because otherwise it would be crossed out. Now this is a surprisingly efficient way to find prime numbers, up until a certain point. You can imagine it would be pretty hard doing this for numbers up to 10,000 and beyond. And it takes years sometimes to trial dividing a number by every number smaller than it, so prime numbers have forever been a fascination for mathematicians. So much so that even now, there are prizes for discovering the next biggest prime number. Currently, the biggest prime number is 24 million digits long. No, not 24 million, 24 million digits long. Like, 1 million has 6 zeros, so it's 7 figures long. So think about how massive this number has to be. And then think how long it would take to try dividing it by every number up until that. Yeah, it's like that famous quote by Hendrik Willem van Loon. High in the north in a land called Svadjod? I cannot pronounce that word. Anyway, there's a mountain there. It's 100 miles long and 100 miles high, and once every 1,000 years, a little bird comes to this mountain to sharpen its beak. When the mountain has thus been worn away, a single day of eternity will have passed. But that was a beautiful digression. Sorry, I love that quote about infinity, so I like to sneak it in whenever I can. Anyway, we're talking ludicrously large numbers here. But the cool thing is, if you were to discover a prime number that is more than 100 million digits long, you'd be awarded a cool $150,000. Sounds a bit Dr. Evil, doesn't it? 100 million digits. Speaking of which, if you figure out a prime number that is 1 billion digits long, you get $250,000. And you thought there was no point learning maths in school. Turns out you can get hella rich from maths. Anyway, nowadays, we have the magic of computers to help us calculate these ridiculous numbers. But the funny thing is that even computers take months and months and months to do these calculations. So the sieve of Eratosthenes is still used as a way to benchmark computers just because we know how long the calculation should take. It only goes to show how damn clever mathematicians have been to do all of this work in their minds and on paper up until now. Alright, so before we really nerd out and talk about the different ways mathematicians and computers discover new prime numbers, let's go over something even more important and interesting. What's the point of prime numbers? I mean, sure, a lot of pure mathematics is about the quest for the underlying truth of the universe. But for most people, that's just not interesting enough. So let's take a short break, then when we're back, we're going to talk about some of the exciting applications of prime numbers, such as cryptography and cicadas? What? Well, you'll have to stay around to find out what cicadas have to do with maths. And we're back. Alright, so by now you probably have an appreciation for how hard it is to find really large prime numbers. It's kind of funny because mathematicians give really exciting names for these, such as monster prime numbers or gigaprimes, which sound like Godzilla monsters. The other interesting thing about primes are that, to date, we've not found a single pattern to the distribution of prime numbers. I mean, we know that as the numbers get bigger, the prime numbers get more and more spaced out, because the chance of the number having another factor increases. But other than that, there's no reliable way to predict where the next prime number will be. This means that they're pretty useful for generating random numbers. If you're a gamer, you've definitely heard of random number generators. Well, many of these RNG algorithms use prime numbers as a base for generating a random number. This is really useful for video games, but also vital for programming and simulations, which many fields of study rely on. And yes, technically, they're pseudo-random number generators because they need a seed number, but we won't go into that too much. Now, the other application of large prime numbers is using them to encrypt data. Prime numbers are really hard to find, but it's just as hard proving that a number is not a prime number. So if you take two really big prime numbers, multiply them, then you end up with a pretty complex colossal number that can be divided, but only by the exact prime numbers that you used. What this means, in simple terms, is that you can create a mathematical lock and key. If the lock is the product of two prime numbers, then you can unlock it if you know one of the prime numbers. Because you can divide that big number by the prime number and you should be able to get the other prime number. Make sense? But if you don't know either of the prime numbers, then it will be really hard to find the prime factors. That is, the two factors that are prime numbers. This is the basis of many different modern cryptography systems, which are systems that we use to turn data into secret codes, so that only people that hold the key can read the data. You can imagine this is extremely useful in the modern world, where the bulk of our communication, data storage, and personal information all live in the digital space. If you listen to episode 22 on cryptocurrency, you'll know that Bitcoin relies on cryptography to generate value for the currency. This encryption system also uses prime numbers. The most famous example of prime number-based cryptography is something called the RSA key exchange. It works like this. Say Alice and Bob want to chat online, but they want to do it discreetly and securely because they want to talk about all the latest goss without anyone else listening in. So to do this, they need to encrypt their message before they send it to the other person, who can decrypt it to read it in plain English. Now this would be easy if Alice and Bob can meet face to face, they can just agree upon a key and lock and then use that system. But if they've never met face to face, how can you share the encryption and decryption codes without revealing the way to decrypt it? Well, what Alice can do is she can take two really big prime numbers, multiply them together, which generates a huge number. The actual maths is even more complicated, but you don't have to know the exact details. Anyway, this huge number acts as what we call the public key, which she can share safely online to Bob. Even if someone was to steal that public key, it wouldn't matter. The public key is just used to encrypt messages, so even if you had it, you couldn't break the code. So Bob takes his public key, then encrypts his message using it. We'll talk about cryptography and ciphers and all that in a future episode, but essentially he's turning his English message into a string of numbers that can only be converted back to English using the private key. It's as if Alice is sending instructions to Bob how to make a lock for a safe for the message with the public key. Bob can then make a safe, put his message in, and lock it, but no one can unlock the safe unless they have the private key. Now the cool part is that the private key is the prime factors of the public key. That is, the two prime numbers that Alice used to make the public key. So because she has the private key, Alice can easily decrypt and decode the message. Presto, secret communication enabled. Now let's say that naughty Eve wants to eavesdrop on this conversation. And she even knows the public key because she saw the message Alice sent to Bob. But if she wants to break the code, she needs to figure out what the two prime numbers made up the public key. And as we know from before, it's redonkulously hard to do this maths, because even if you have a bunch of supercomputers, it would take months or even years to find the prime factors by using brute force maths, which makes the RSA encryption really secure. Woohoo! Go maths! Letting us have sneaky chats and have decentralized virtual money based on memes. One more thing on cryptography. There's a possible future where all of this becomes meaningless, and that's when quantum computers become a thing. These are a completely different kind of computer that's being developed, which may be able to do calculations so much faster than classic computers that they could break prime number-based encryptions in a reliable enough time in the future that things like RSA encryption wouldn't be secure enough. but fortunately they seem to be a long way away enough that we don't have to worry about them for now. Now, let's get to the topic that I'm sure you're all here to learn about: cicadas. If you live in Canada or the USA, you might know that on some years, summers become insanely loud with a lot of cicadas suddenly popping out of nowhere. Where are they coming from? Sprouting from the ground or something? Well, actually, kind of, yeah. Since the 1700s, we've known about a few species of cicadas known as periodical cicadas, who like to emerge in massive swarms at certain periods. The weird thing is, these cicadas have really long life cycles, taking either 13 or 17 years to fully mature into adult cicadas. Until then, they lie underground sucking sap from tree roots for over a decade. Then when the time comes, they all rise, filling the air with their majestic cries, telling all cicadas around them to come and bang them. Yeah, nature gets real sexual, because apparently that's the point of life according to evolution. Hang on, 13 and 17, do they divide into any other factors? No? Oh, mate, they're prime numbers. Is that just a weird coincidence? Maybe, but it's weird how specific those numbers are, so there's probably more to it. The leading theory on why periodic cicadas have 13 or 17-year life cycles is a well-documented survival strategy called predator satiation. Some species survive by being the strongest, toughest mother lovers, with scary fangs and talons. Some species get really good at running away at breakneck speeds. The humble periodic cicada survives by producing so many offspring that no predator could eat all of them. No, seriously, it's a legitimate strategy that works for many species. Turns out nature doesn't care about how many of your kind dies, as long as some survive long enough to breed. It's like making so many cookies that even if your girlfriend snuck into the cookie jar to steal some, you'd have plenty left over, because even she can't eat that many cookies all at once, right? But there's one flaw in predator satiation. What if another predator species happens to line up their life cycle with your life cycle, so that they have a population boom thanks to an abundance of food every time you emerge from the ground? That would be disastrous. And this is where the magic of prime numbers comes in handy. If you reproduce and emerge every 13 years, then there's no other number that neatly divides into 13. Let's use some examples to illustrate the point. Let's say, just for argument's sake, squirrels take 2 years to mature, owls take 3 years to mature, and cats take 4 years to mature. This means that every second year, you'd see a boom of squirrels running around, hunting for insects. Since cats take 4 years to mature, every second cycle of squirrels maturing, the cats get to feast on squirrels, like a squirrel buffet. This would eventually cull a lot of squirrels, endangering the species. And worse yet, every 6 years, the owl's life cycle overlaps as well, so the squirrel population could be decimated. But in the periodic cicadas case, because they come out every 13 or 17 years, both prime numbers, there's no other animal that could take advantage of their maturity cycles. Because also, not many animals take 13 to 17 years to mature, looking at us human beings. Now the whole thing gets even cooler when you dig one level deeper. If you have one cicada species that takes 13 years to mature, and another species that takes 17 years to mature, then make them kiss and have babies, then you might end up with a hybrid cicada that takes 15 years to mature, just the way genetics work. This is called hybridization, which sometimes leads to cool new adaptations, but in the case of periodic cicadas, it might ruin their awesome mathematical survival strategy. Well, since both 13 and 17 are prime numbers, it would be very rare for there to be a year where both species of cicadas are popping out to breed. This reduces the risk of hybridization, which in turn means that the cicadas are more likely to survive and maintain their traditional Amazon Prime lifestyle. I love the story of periodic cicadas because it's an example of how fundamental mathematics is in the universe. Hell, Galileo called mathematics the language in which the universe is written, and we certainly see examples of weird mathematic rules popping up all throughout nature. And that, as Finn the Human would call it, is pretty damn mathematical. Alright, now that I've totally convinced you that maths is awesome and prime numbers are super interesting and cool, how can we find more of them? Let's get real nerdy here and do some maths. So, like we talked about earlier, mathematicians had to work out by hand whether a number was divisible by any other factor to prove that a number is prime. But after a certain point, the number becomes really big. So, for example, the largest prime number proven by hand was proven by Edward Lucas in 1876. This number is so long that it has 39 digits in it. This means that it's in the realm of 100 million 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 million. It's really, really big, okay? Anyway, it took Lucas 19 years of testing to finally prove that that number was absolutely a prime number, no question. Now, Lucas was a brilliant mathematician, so he didn't just test every number less than this number. He only lived till 49, so that's like 2 or 3 primes that he could have tested in that time anyway. So how did he come to this weird big number? Well, you see, even though there are no set patterns to prime numbers, mathematicians figured out a while ago that there are some types of numbers that are likely to be a prime. The most famous of these are the Mersenne prime numbers, discovered by Marin Mersenne in the 17th century. He discovered that a lot of prime numbers take the form of 2 to the power of n minus 1, where n is a prime number. So for example, if n equals 3, a prime number, then 2 to the power of 3 is 2 times 2 times 2 is 8. Minus 1 is 7, which, hey, is a prime number. But there are also numbers that follow this formula and not a prime number. Like the next one, 2 to the power of 4 minus 1 is 15, which is definitely not prime because you can factor it by 3 and 5. But using this formula, you can generate some likely candidates, which means you can skip some numbers before you test a number to see if it's prime or not. Now, Lucas went one step further and came up with a test that would predict to a high likelihood whether a number is prime or not. This was later revised by another mathematician, and now it's called the Lucas-Lemma primality test. If math gets your freak juice going like me, then I'll link a really good video that you can watch explaining this test in the show notes. But in fear of potentially putting the other people to sleep while driving or doing chores while they listen to podcasts, let's not go into the details of it right here. Anyway, these tests and algorithms that brilliant mathematicians have devised are really useful, because now we have machines that can run thousands to millions of calculations at an instant, so they can crunch through massive numbers using the algorithms at much faster speed. Yay for computers! All the biggest prime numbers that have been discovered since 1876 have used either calculators or computers. That's how we discovered ludicrously large prime numbers like the Mersenne prime 2 to the power of 82,589,933, minus 1, the current record holder. But funnily enough, we already know that there is an infinite number of prime numbers. This means that in the grand scheme of things, even this gargantuan number is piddly compared to the rest of the numbers we haven't even discovered. Isn't that crazy? What's more, the person that figured out that there's an infinite number of prime numbers lived 2,300 years ago, before algebra was even invented. Think about that. This man, of course, is the father of geometry, Euclid of ancient Greece. Euclid wrote about a fascinating theorem in his foundational textbook, Elements, that talks about how there must be an infinite number of prime numbers. I know we've covered a lot of maths already, so I promise this will be the last one. So Euclid's theorem goes like this. Let's say that we have a finite set of prime numbers. An example of a tiny set would be 2, 3, 5, 7, and 11. Now, take all of the numbers in this set, then multiply them to each other to make the product p. So in our case, p would be 2 times 3 times 5 times 7 times 11, which is 2,310. Then, we'll be real cheeky and add 1 to p, making a new number, q. So if p is 2,310, q would be 2,311. Now, according to Euclid, if q is a prime number, then that means there is a bigger prime number than the ones in your set of prime numbers. Because q is by definition a bigger prime number than any of the numbers you listed, right? So, if q is a prime number, then yes, there is a prime number that exists outside of this finite set. Cool, easy. But if q is not a prime number, then there must be a smaller prime number than q that divides q and p, by definition. This is because if a number isn't prime, then it must be divisible by another factor, one of which has to be prime. And because q and p are one number different, there can't possibly be a number that divides both p and q without leaving a remainder of 1, because the only number that divides 1 cleanly is 1. Therefore, this set must be missing a prime number. There's some other prime number that has to divide q and p. And this means that it's not a complete set of prime numbers. If you keep expanding the size of this finite set with more and more prime numbers, there's always going to be one of two outcomes. Either q will be a new bigger prime number, meaning that there is another prime number somewhere, or it won't be a prime, meaning that you missed a prime number somewhere in the set. It's a bit mind-boggling, but it essentially proves that there must be an infinite number of prime numbers, because you can't have a finite set big enough to include all the prime numbers in existence. I'll link another great video explaining this in the show notes, so you don't have to think about it too hard. I thought it would be interesting to share this because Euclid figured this out 2,300 years ago, when proper algebra using multiplication and division didn't exist. I mean, the concept still existed, of course, but it hadn't been properly discovered and codified yet. And that's mind-blowing for me, that we are here where we are now, landing people on the moon, having the technology to send cat videos instantaneously to other people, and calculating how much money we can save when something is on sale. All because we stand on the shoulders of very clever giants before us. And maybe that's what the real beauty of a prime number is. Not only do we use prime numbers to encrypt messages, to do quantum physics, to make random numbers, make computer screens, figure out cool evolution tricks that cicadas use, but they're also a reminder that for millennia, humanity have continuously strived to uncover more truths about the universe, trying to understand how everything works, unveiling the mysteries in the world around us. And that's why prime numbers are important. They're a symbol of the noble quest for knowledge and understanding. And yes, you can feel clever and smug, and that's kind of cool. Alright, so what did we learn today? We learned that prime numbers are numbers that can only be divided by two factors, the number itself and 1. We learned that prime numbers can be really hard to discover as numbers get bigger, because it takes ridiculous amounts of calculation, even using computers. This lets us use prime numbers to encode secret messages through encryption, and they're really hard to break. We learned that cicadas also use prime numbers to avoid predators synchronizing with their life cycle, letting them flourish and survive without getting completely eaten up. We learned some fascinating maths such as Mersenne primes and Euclid's theorem, so you can sound smart to your friends and maybe win some pub quiz points. Lastly, we learned that maths is awesome and you should never stop your pursuit of knowledge, nerd. Okay, for today's 2 Minutes Explain, I thought we'd tell you about something completely off topic from maths, because you probably have numbers swirling around your head like that gif from The Hangover. So instead, let me ask you this. How could you eat 100 eggs in one sitting? Don't worry, it's not a trick question or a maths problem. Well, you can try and name all the different ways of cooking eggs, like fried eggs, scrambled eggs, poached eggs, or boiled eggs. Oh god, I'm getting hungry now. But all of those options would still make you explode from eating too many eggs. 100 eggs weigh 4 to 5 kilograms, containing about 7,750 calories, which is more than triple the recommended amount of calories you should consume in one day. Not to mention the amount of cholesterol that it would contain, that it would probably immediately give you a heart attack somehow. So, how can we stuff 4 to 5 kilograms of eggs into our stomach? Well, we can use the power of science! The secret method of cooking to eat 100 eggs turns out to be noodles. And not just any egg noodles, though. We're not going to be making dough, because that would still be a massive amount of food. Instead, you could take 100 eggs, crack them into a massive basin, whisk it thoroughly, and boil up some water in another big pot. Then, take the egg mixture and pour it through a sieve straight into the boiling water. You'll notice that the proteins in the egg will immediately solidify into thin, long noodle shapes, while the water disperses out into the rest of the pot. This leaves you with all the goodness of 100 eggs in a manageable amount of noodles that can actually fit in one bowl. Because turns out the bulk of the weight and volume of eggs, about 2/3, is water, much like us, and all other living things. All the other methods of cooking eggs trap the water in the final form, whereas the noodle method concentrates all the goodness of the egg into a fraction of its original weight, without wasting stomach space on water. But, of course, at the end of the day, you're still eating 100 eggs, which is a lot of calories and cholesterol, so don't do this at home, kids. Well, that's it for today. Thank you for listening to Explain This. I hope you've learned something interesting and maybe even useful today. Maybe it'll make you nerd out on maths a little bit and look up things like Fermat's last theorem or the Riemann hypothesis. Or maybe not. Either way, we'll see you next time. Bye for now. Explain This was written and hosted by me, Jin Kim. If you'd like to suggest a topic or just send a lovely message, you can email me at explainthiscast@gmail.com or follow me on Facebook or Twitter. Now, around that time, another mathematician called Eratosthenes